Okay, so welcome to everyone. I hope you had time to go through yesterday's class again, so everything is fresh in your mind. As I said yesterday, today what we are going to do is we are going to extend the analysis we did yesterday for one species to more than one species. So remember that the question that we were trying to understand is why are species that in principle compete to each other, why they are able to live together. So why, despite this fight and this struggle for survival, they sometimes live happily together in the same place. Remember also that we are going to do that in a very humble approach. We are going to take a very, very simplified picture of this competition, and we are going to consider very few species. In the real world, as you can imagine, this is much bigger problem, and the techniques that people use rely on the ones that we are seeing, but they are not exactly these ones. We are going to discuss that also a little bit at the end. And if you have questions, we can have a brief conversation on that. I'm hoping to finish a bit earlier today in case we want to talk a little bit more about real world scenarios and forget the blackboard and the math a little bit. So remember that something that yesterday was motivating us was this kind of growth curves that we saw experimentally in ghost experiments. Today, what we are going to do is to revisit a second set of experiments that he also did, where the only thing that he did new was to mix the red and the blue cells, so to say. So he mixed the two different types of yeast that he was working with. So this is what is shown here in this figure. You can get the original curves from this reference here. The only thing I did was to more or less by eye, I took the experimental points and I represented them again, but it's pretty much the same. And here you can see that we still have the curves that we saw yesterday. The ones in more intense color are for solitary growth, the same that we had before, but now put in a different plot. So you can see more clearly the different scales that we were mentioning, both in population size and also the temporal scale to get the saturation and all the ideas that we discussed yesterday. But now the other thing that I am adding, and I'm going to make this bigger so you can see it more clear, is that I'm adding a second collection of points that are these less intense blue and red points. So these points correspond to the growth of these cells when they grow together. So the only thing I'm doing now is I'm putting a little bit of red and blue cells initially in a bottle with my sugar for them to grow, and I am allowing them to grow until they kind of stabilize. And what you can see already from this very simple experiment is that, I don't know if contrarily to what you were expecting, I was, for instance, expecting to see that maybe only blue cells will survive because they will kill all the reds, or the reds would kill all the blue. But what we see is that they all reach a kind of a stationary state where they coexist. So what we are trying to understand today is what's happening here. So these two types of cells can coexist, and whether this is something general or not. For instance, if I take two different types of cells that are different to these two, will I expect this? Do I have different outcomes? What's the mechanisms behind this growth process that is driving this result? We're going to develop a very, very simple model to understand this behavior and also to predict other possible outcomes. That's something that is very important when one does models in biology or in epidemiology, in ecology, or models in general. We don't only want to explain experimental results that we have, we also want to try to make predictions to hopefully guide new experiments. So for instance, I may find with my model that red cells can kill the blue ones if some conditions are met. And then I can come back and I can talk not to Gauss, because unfortunately, well, he passed away many years ago, but with some experimental colleague, and I can tell them, look, I found this in my model. My model is explaining your results, but in a different regime is predicting this other different behavior. Maybe you want to look into that and see if you can confirm my theory. So this kind of conversation between models and experiments is something that, at least to me, is very, very fun of doing this kind of research. And I think it's one of the reasons why more and more people are enjoying this type of work every day. So let's go to the Blackboard. Today I try to make it larger so it's in the screen. It occupies more screen, but it also has a lot of space, so we have a lot of calculations there. Let's see if it works, and more importantly, if I manage to to not mess things up a lot. So remember that yesterday we had our cells. Let's put here other color. I don't think black is going to be very useful. So we had our cells that were in a bottle, and we had all black, white cells. These white cells, initially we assumed that they were only reproducing, dying. Yes, sorry, something that I have to tell you guys is that today, I don't know, someone decided that this was the best time to do a construction upstairs, and it can get very noisy. So nothing I can do. I can only speak more louder and try to be more noisy than the machines up there. So something else that we also assume is that there is some death. Remember that with these ingredients, we came out to the conclusion that the model was purely linear. And to recover the experiments, we needed this additional process that was basically what we called competition. So two cells of the same type encounter to each other, and one kills the other. Now, of course, the picture is a little bit different because I don't only have white cells, I also have pink cells. And this is going to open a lot of new different processes, many new different processes. So basically, it's going to at least multiply it by 2. So I'm going to have reproduction of pink cells. I'm going to have death of pink cells. I'm going to have encounters between one pink cell and a second pink cell that are going to result in death. But now I have 2 more processes, right, that are the cross-species processes, if you want to call it that way. We are going to put the proper names now in a minute. So what we have now is that a pink cell may encounter a white cell, and this may lead to the elimination of a pink cell. And in the same way, we may have that a pink cell encounters a white cell, and this results in the elimination of the white cell. So this is a different form of competition, different to the one that we saw yesterday. This is called, interspecific competition, because it happens between species, across species, and the ones that we saw yesterday, pink with pink and yellow with yellow, are called intra-specific competition. Okay, inter and intra, not very hard to remember. So at the end, what we are having is these 2 different species of yeast, or these 2 different types of cells, the white ones and the pink ones, that are living together in this bottle. And we have that the presence of the white type of cells inhibits the growth of the pink type of cells, and the other way around as well. And this is just a schematic way of representing this, this interaction using something that will come a little bit later, but I already want you to introduce that is a kind of network representation, where I'm going to use these nodes or these balls to represent the species. And I'm going to use these links or these lines to represent interactions between the species. When the interaction is negative, I'm going to use this end for the link, this end for the interaction. And when it is positive, I'm going to use the typical arrow that you will see in a while. In this case, it's inhibition, inhibition. So I'm going to represent this interaction in this way. So Gabriel is asking if the competitive factor can be inserted into the death ratios, considering competition, the death ratios changes. So Gabriel, that's a very good question. What I can do, I'm being very, very explicit here because I want you to have all the processes in the paper. What I can do, as you already probably thought yesterday, is I can merge these two processes together by defining an effective rate, which would be the difference between the B that I was using yesterday and the B that I was using yesterday. I can kind of rescale this process. What I cannot do, I cannot incorporate this death rate into this competition because, as we were saying yesterday, these are, one is a linear process, the other one is non-linear. I mean, you can write them together. In terms of writing, you can write it together. You can say processes that contribute to the elimination of one cell. And you can say this happens at a rate D plus the square, the quadratic term that we derived yesterday. You can do that if that notation is more convenient for you. But they are different processes, and it's not so easy to rescale as it is to rescale these two ones that we saw yesterday. Okay. But in terms of notation, yes, if for you it's easier to consider an annihilation process, everything that ends up with one cell less than with elimination of one cell, and you can write it as a combination of a constant plus a quadratic term, you can do that. There is nothing impeding you to do that if you are able to find the processes that way. But they are fundamentally they are different. Remember, one is linear and the other one is non-linear. So the key processes here, or the new ones, everything is together in the left block, in the center block. What is new is these two new processes here on the right, that I'm going to label them with two rates, let's say gamma 1, 2 and gamma 2, 1. Saying that one of the species is going to be the species 1 and the other one is going to be the species 2. So to introduce some notation that we are going to use today, in general, these coefficients or these rates gamma ij are going to be the rate at which a species j inhibits the growth of I. So let's have it clear that the second index is going to inhibit the first. Okay, I'm going to try to have it clear as well, but to me, everything that relates to indices, order, it's very hard. It's very tricky to keep focus and keep track of which order is the which index is the second, which one is the first. So probably that's the reason why I'm not working in general relativity. But let's try to do it, and let's try not to make any mistake. So with this, now what we can do is nothing else than what we did yesterday. We can write a master equation for our probability. Of course, now the probability is not as easy as yesterday because now I have the probability of having n cells from the species 1 and n cells from species 2 at time t. And let's say, I don't know, that 1 is the white one and 2 is the pink. Although that's not so important. So now my probability is, of course, two-dimensional. I have two variables. It's a bivariate probability distribution function because I have more than one species. So now, if you want to define the mean number of species of cells from the species 1 at time t, you have to take into account that to calculate these mean values, you have to use the definition of the mean value when you have a two-dimensional probability distribution function. So for instance, if you want to calculate the mean value of n1, this is going to be equal to the sum from n1 to 0 to infinity and n2 from 0 to infinity of n1 p n1 n2 t. This is just the extension of the definitions we saw yesterday to two-dimensional cases. So if you want to, once you obtain your master equation, following the same steps that we followed yesterday, but remember that now you have 8 processes. So your master equation is going to be much more fun. It's going to be much larger. The easy thing is that the rates are pretty much the same. In this case, it's just an encounter between N1 and N2. And in the other case, it's going to be N1 with N1. So the rationale is the same. The algebra is different. So you maybe have to sit down and do the algebra carefully and follow all the steps, but you won't find any problem. And if you do, you can ask me tomorrow. I will be online a bit before the class, so you can write me an email. We can discuss that. But the algebra is algebra. So I don't want to spend a lot of time doing algebra. I prefer to discuss ideas with you. So of course you will get an equation for the mean value of N1, the mean value of N2, as we obtained yesterday doing this algebra. And now the thing is that our system of equations, instead of being one-dimensional, is two-dimensional. I will have let's do here after obtaining the master equation and doing mean field approximation. Remember that we have to also do this mean field approximation. What we get is a set of equations for N1 and N2. And I'm going to remove these braces from the notation just to save a little of notation. And I'm going to also, let me make here a note for those of you that are not so familiar with math. I'm going to use this notation, okay? The dot in top of the, yes?
May I ask something?
Sure, of course, Lucas.
When you make the mean field approximation, does it mean that the competition are short-ranged?
No. So if we remember, if well, you remember from yesterday what we discussed, so the competition, we are going to assume that always it's short range. So when we derive this, luckily I have it here. Let's jump quickly. So if you remember yesterday, when we derived this quadratic form for my encounters, what I assume is that this green cell that I was giving some privileges to her in the beginning, it interacts with any other cell in the neighborhood, and this interaction is proportional to the density. When I assume that, I'm already assuming that the interactions are not only short range, but local. I'm assuming that they need to collide. This is like the same that you assume in the law of mass actions of chemical reactions, or when you work with collisions in between particles. So this is already telling me that it is short range. When I do the mean field approximation, what I do is eventually in my equation, I will get that my mean value of particles, the mean value of the number of particles, depends on the mean value of the square. The mean field approximation basically is neglecting fluctuations, we said yesterday, okay? So two different things. We will see in the last class, we will see what happens when we have long range competition. That's the topic of my research, and I want to show you a little bit what happens and the funny things that happen. Some self-promotion, I always like doing that. Anyway, so after doing this and moving to this notation, what I get again is an ODE for N1 and an ODE for N2. If you do all the calculations, all the math, you will get to something like this, and I'm going to explain now my notation a little bit. So this is the system of ODEs at which you will arrive. Let me put a frame to it. Where I'm only, if you remember from yesterday, I'm only defining R sub I as the difference between the V and D that we had yesterday. And here, these gammas are basically following the definition that I introduced already here. gamma 1, 1 is the intraspecific competition between species 1. So it is how species 1 inhibits herself. 2 is how species 2 inhibits 1, and so on and so forth. Okay, so we have our system of ODEs, to which in principle we can do things that are much, we can do more things than to the master equation. But now there is a problem that will happen many, many times when we work with models of not only biology, ecology, sociology, with models of the real world. And the problem is that now this system of ODEs has six parameters. And that's problematic because how do we start? Okay, you guys can tell me, oh, you can measure this in the experiments and you can put some, or you can ask to, okay, that's an approach, but sometimes measuring parameters is not so easy. Most of the times, I would say. And there is something else, and it is that if we want to run a general analysis of this problem, we want to somehow cover all the parameter space. We want to find new behaviors. Remember that we want to predict. So the fact that a specific system has this value for R doesn't tell me that in some other case I may have a different R and I have a new fun and interesting behavior. So we want to kind of be systematic here. There are many things. Well, there are ways to do this, and usually what we are going to do is to reduce the number of parameters by working with what is called non-dimensional variables and non-dimensional parameters. So what we are going to do is to non-dimensionalize the system. This is very convenient because it reduces a lot the number of parameters. It makes things more manageable. It's also not so easy because it depends a lot on the hand of the artist. This is a direct translation from Spanish. It depends a lot on intuition. On if I define time in this way, maybe I get rid of one parameter. If I don't, maybe this is not so clear. So there is no a universal recipe to do non-dimensionalization of dynamical systems that will simplify things. The more you work with this, the more intuition you develop, and the more by looking at the structure of the equation, you say, this is like this, or if I do this, I get rid of everything. So it's a matter of reading, practicing, studying, and doing it. Sometimes it will be better, sometimes it will be worse. So before we move to the non-dimensional version of this system, you may also, this is just rewriting the equations, but you will very likely find this system written in this way as well in the books. So let me put it here also because it's going to help us a lot to get the non-dimensional form of these equations. So let's do this intermediate step. Sorry. So here the only thing I did was kind of it was to rewrite these equations in a logistic way. Remember that yesterday we got to this description that was having all the rates explicitly with each of the terms from where they come microscopically. Now the only thing I'm doing is taking this outside and then redefining the case and the gamma. So here in this from this step, what I'm doing is K1 is equal to R1 gamma 1, 1, and K2 is equal to R2 gamma 2, 2. So it's a matter of rewriting the equations. So I have current capacities and I have ratios. Sorry, I have current capacities and I have ratios between species strength interactions. This is going to help me. I mean, this is kind of an intermediate step to write a non-dimensional version of these equations. But there are some books that will present you this system of equations already written in this way. It's the same. It's a quadratic term with cross terms. It's just a matter of writing things in a way or in another. And final thing I can do, of course, many of you are probably imagining that is I can define, and I'm going to write it here once more, I can define alpha 1, 2 as equal to gamma 1, 2 over gamma 1, 1, and alpha 2, 1 equal to gamma 2, 1, gamma 2, 2. So notice that I'm respecting the order of these indices here to put them into alpha, and because the denominator is always with the same index in the two places, I'm keeping it. So basically, with this definition, I can write it this way, and this is the way where you will find this equation most of the times, written in terms of the current capacities, which remember is the maximum population size that each of the species will reach in the absence of the other species. So if I set N2 equal to 0, I recover the logistic growth we got yesterday, right? You can see it there. The same for this expression. So K1 will be the current capacity of species 1 without the species 2. And the second parameter, alpha 1, 2, is the ratio between the intensity at which species 2 inhibits species 1 and species 1 inhibits the growth of herself. So this is a way of rewriting the equation with parameters that have another interpretation, more in terms of current capacities and relative interactions between species. At the end of the day, this is mathematical ways of writing this microscopic process, okay? Nothing, you sit down, think carefully, and you will get to the point. I did, so nothing very, very hard for you guys. So the last is now we have this equation that is written in this more I don't know if direct, but at least more common way. And what we can do is to finally define what are going to be our non-dimensional variables and non-dimensional parameters. So we define non-dimensional variables and parameters. As I said, this is going to depend a lot on your hand and your experience and your intuition. In this case, the one that is going to help a lot is if I define U1 as being N1 over K1, U2 equal to N2 over K2. I'm going to define a non-dimensional time that is going to be R1 times the dimensional time. Remember that R1 has units of the inverse of time. I'm going to define a non-dimensional rho that is going to be the ratio between R2 and R1. And finally, I'm going to define a cross-species non-dimensional interaction strength that is going to be the non-dimensional version of this alpha 1, 2 and alpha 2, 1. That is going to be equal to alpha 1, 2 K2 over K1 and A21 equal to alpha 21 K1 over K2. So I said something wrong. Alpha is already non-dimensional, sorry, right? Because it's the ratio between two gammas that have the same units. What I'm going to do is to somehow incorporate the weight of the current capacity in this in these new non-dimensional parameters. So as I said, this may sound to you like magic, like I'm defining some magic, taking it from my hand. In part it is. I mean, you could come up with any combination of non-dimensional parameters that maybe will simplify the equations in a different way, and you will need to repeat the analysis in a different way. But this is the one that works the best for this system, and is the one that you will find in all the textbooks and all the studies with this model. So once you substitute these non-dimensional units here, these non-dimensional units into your equations. So for instance, if I want to calculate the derivative of n1 with respect to t, I would need to substitute n1 by u1 times k1, right? And I would need to substitute t by tau over r1. And then I would get the derivative of u. Okay, I'm going to do it once because I think that may help everyone in the room. Let me copy this because if not, I will do something wrong. So these are our non-dimensional units, the variables and parameters. Sorry. If I want to if I want to write the derivative of n1 with respect to t in terms of these new variables, what I have to do is I have to consider that n1 is equal to u1 k1. And I have to also consider that t is equal to tau over r1, right? So then I plug it here, the derivative of n1 with respect to k, this derivative is going to be k1 derivative of u over derivative of tau r1. Everyone follows this? K1 is constant, that's why it goes out of the differential. This is a physics way of doing this. If there is any mathematician in the room, you can mute your headphones and we can see you in 30 seconds once I write the non-dimensional equation. But this is pretty much the same. And for the right side, I would eventually have
You wrote an index 1 at the tau letter.
Ah, yes. This is very me. Thank you. And then I will have, I will have this right side of the equation. That you guys will need to now change. You can, you will substitute this n1 by u1 k1. This r1 stays the same. Now I have a1. N1 over K1 is going to be U1. Alpha 1, 2 is going to be A1, 2, K1 over K2. And N2 is going to be, sorry, I'm doing something wrong. And N2 is going to be K2 over U2. Basically, this is going to cancel with each other. This is going to cancel with this. And I'm doing something wrong where I'm missing the, no, I have a K1 here, and this one goes out with this one. And at the end, what I get is U1, 1 minus U1. Sorry, I'm trying to be fast, but I think it's better to do it well. So what I have is U1 times 1 minus U1 minus A12 U2. And this is equal to this here, which is the derivative of U1 over tau without the index. So as you can see, what I got by working with these non-dimensional parameters and units is that my equation now only depends on one parameter. I get rid of everything. I didn't get rid of it. I condensed it in these non-dimensional units. Okay. If you repeat the same for the second equation, I'm going just to close here this side note. What you would get is that let's write in an elegant way this first equation, pretty here. So we are proud of it. 1 minus U1 minus, and So this is what you will get if you repeat this substitution that I did here in a very rough and dirty way for the second equation. The take-home message is that now we have half the number of parameters. Instead of having 6, we have 1, 2, and 3. And these parameters also have some meaning behind them. So this A12 and A21, remember, is this ratio between the strength of the competitive interactions, and this rho is the ratio between the exponential phase, the phase of is the ratio between the rates of the exponential growth phase. Remember that it was R1 over R2. So they have meanings. They have meanings that we have to just elaborate and familiarize with them, but they allow us to still make some reasoning, and that will become more clear in a little bit. So now what we can do is basically what we're going to do is repeat the analysis that we did yesterday for one-dimensional systems. I'm going to call to this function f1 u1 u2 and to this function f2 of u1 u2, and we are going to analyze this system in a while. Before doing that, I want to know if you guys have any questions that want to ask. Nicolas, yes, so Nicolas is asking if the definition of tau means that we are taking the time scale of n1 into account. Yes, so we are rescaling time. We are measuring time in units of the natural growth rate of species 1. Okay, you can choose species 2. Yes, there is no, that's the hand of the artist, as we said before. Rafael is saying, for this application, is there any text in which the P-Buckingham theorem is presented with more details, analyzing the non-dimensional groups and parameters? My brief answer is, I don't know. Sorry. This is very well explained in Steven Strogat's book, as I said yesterday. There is also Jim Murray's book on mathematical biology that does this for many models. A place where it's defined in a more rigorous way, I'm sorry, but I don't know. Vitor Hugo is asking if defining non-dimensional variables is useful to decrease the number of parameters. Do they help in something else? Well, it reduces a lot the dimension of our parameter space. That's a very, very useful thing. Sometimes also, if you rewrite the system in this way, you get to know if one of the time scale, for instance, if one of the populations grows much faster than the other, and you can do things like elimination of fast variables, assuming this, I think the name is in English is adiabatic elimination of the fast variables. So you assume that one of the species is in the stationary state and all the dynamics happens in the second dimension. You can do other things. And well, everything else we have are codes. So guys, if you have questions, you can also raise your hands and speak them.
Ricardo.
Yes, Pedro.
One quick question. If you take the tau scale based on N2, the raw parameter will be in the U1 equation, right?
Yes.
Okay, perfect.
Yes. We will see in a while that actually this is even better because we have 3 parameters. Let's write it here. But one of them is going to be not so important. And rho is going to be the one that is not so important. So that's double good news. So what can we do to this system? Well, the first thing that I think you guys are thinking of doing is to calculate the fixed points, as we did yesterday. Fixed points of the system, which are basically the values of U1 and U2, for which F1 U1 U2 is equal to 0 and F2 U1 U2 is equal to 0. So anyone wants to shout them out? I can tell you the first one, for instance, is 0, 0, right? By making this one 0 and making this one 0. There are other almost trivial fixed points that are 1, 0, and 0, 1. This can also be done by eye, but there is so let's put numbers. How can we do this? Sorry. The first one, the second one, the third one. And sometimes there will be a fourth one that basically is going to be one where I have some U1 star and U2 star, where none of them is equal to 0. So that basically, as many of you are already thinking, it will come from solving these two things to be equal to 0 at the same time. So what we are going to do next is to calculate the stability of each of these fixed points. We are going to see what is the ecological meaning of this, and we are going to see if we can generalize this calculation in a way that we can be more systematic. That's what we are going to do until the end of the class. So this fourth point that I want to calculate, that sometimes will appear, as I said, comes from solving this. And if you solve this, what you will see is that U1 star is equal to 1 minus A12 over 1 minus A12 times A21. And this U2 star is 1 minus A21. And of course, to have this, we need that A21 times A12 needs to be not equal to 1, because if not, this denominator is going to be 0, and then this doesn't exist. So already going back to the, as you can notice, guys, today I'm skipping a lot of algebra because I really want to use these two hours to discuss concepts and ideas. But please, if me skipping algebra is a problem for any of you to follow the class, write me afterwards. I have the notes with all the algebra open. I'm happy to take pictures of it and send them to you to go to any detail. Don't be shy, don't feel bad. It's just that I want to use these 2 hours to provoke thoughts in you rather than to go through algebra that for many of you may even be a little boring. So anyway, this fourth point that we have here, as I was saying, I think it's already giving us some hints about these experimental results that we were discussing, because these experimental results that we were discussing show us two stationary values for the populations where none of the species is 0. And this fourth point that we know now that sometimes exists and sometimes does not, is the only one that meets these conditions. So what I want to do next is to find when this fourth fixed point is relevant. Of course, it is going to be relevant when U1 star is positive and U2 star is positive. Why? Because we are working with cells, number of cells. Number of cells have to be positive. For us, in our two-dimensional phase space, or one defined by U1 and U2, it's only the first quadrant, the one that is going to be meaningful for us, because it doesn't have any sense to have -3 cells. So the question that we are going to address in this second hour is what are the conditions for the existence of this point and when it exists, when is it stable? Here, let's say if. So we want to know when it's meaningful and when are we going to observe it. And we are going to observe it only if it's stable, because if it is unstable, I think, guys, you can spend your whole life in a lab and you will not find the unstable point, because the system will not go there, will not go there unless you start the system there. So we want it to be stable. So the approach we're going to use to answer these two questions is the graphical approach we started yesterday, because we are going to see that it is very powerful. It's going to give us a lot of information, skipping a lot of the calculations behind all these systems. And then we are going to formalize it as we did yesterday with the linear stability analysis, and we are going to see how that extends to 2 dimensions. So a concept that appears very important in these 2-dimensional systems is the idea of the concept of the null lines. So when I have my dynamical system that is given by this set of equations, we already said that the fixed points are going to be the points where both these 2 equations are equal to 0. The null lines are going to be the lines or the curves in the phase space. Here I'm already abusing of language because in our case are going to be lines, straight lines, are the curves on the phase space where each of these equations are equal to, each of these functions are equal to 0 independently from each other. Sorry, Ericles, null lines. I'm going to write it more clear. Null lines. So let's calculate them very quickly for our system. So first we are going to calculate the U1 null line. That basically comes from doing F1 equal to 0, and you will see that we are going to have 2 null lines. The first one is U1 equal to 0, and the second one, as I said, is a straight line, U2 equal to 1 minus U1 over A12. And then we can calculate also the U2 null lines that come from solving this second equation, and you will see that this is U2 equal to 0 and U2 equal to 1 minus A21 U1. So as I said before, as I already anticipated before, these null lines do not depend on rho, and that's very important because we have only 2 parameters. And depending on the values of A1 and A2, we are going to have 4 different cases for these null lines. So I'm going to work through one of them more carefully, and then we are going to discuss all the other 4, the results of all the other 3, and we are going to connect each of them with the ecological meaning of them. And I'm going to do the analysis here in our Blackboard to make things easier to follow, and then we will jump to more like pretty and clear figures I did with the computer. So the first case that we are going to study, and I'm going to call it case 1, is the case when A12 is bigger than 1 and A21 is smaller than 1. So you can probably already see that the key point of the key role of these parameters is basically that they are giving me the slope of these lines, of these null lines. So somehow, depending on the slope of these null lines, I'm going to play around with the crossing points, basically. That's the idea for those of you that have a more geometric thinking. But we're going to do it, don't worry. For those of you like me that lack geometric thinking. So let's write our axes, and I'm going to be very careful with them so we get it straight. Perfect. So this is going to be U2, and this is going to be U1. So the first null line I'm going to use, let's see, pink for U1 null lines and green for I'm going to use pink for U2 nuclines and green for U1 nuclines. So U2 nuclines are these ones here. U2 equal to 0 is the first one. And I said I was going to use pink. So let's draw it. Perfect. This is the first one we have. The second one is this nucline here. 1 minus A2 1 U1. So if U1 is equal to 0, sorry. If U1 is equal to 0, this nucline U2 is equal to 1. So I'm going to come here. And I'm going to put here my 1. And when U2 is equal to 0, this nucline here takes a value that is going to be 1 over A to 1, okay? And this 1 over A to 1 is going to be bigger than 1 because A to 1 is smaller than 1. So basically 1 over A to 1 is bigger than 1. So I'm already going to put my 1 here to make things easy. Okay, this is going to be my 1 here. So now I can draw my second nucline that basically is a line that goes from here to here. Let's cheat a little bit. From here to here. Perfect, much better now. And now I repeat the same for the nuclines of U1. And as you can see, the first one is the trivial one. We said it's here. Okay. And the second one, if you repeat the same steps, is going to be a nucline that goes, takes up, it's equal to 1 when U2 is equal to 0, and it's equal to 1 over A1 to when U1 is equal to 0. So you can obtain that from this equation, basically. So we can draw it this way. Perfect. So now, what are the fixed points of this system? We said that the fixed points are the points where both nuclines are equal to, when both functions f1 and f2 are equal to 0 at the same time, right? So basically when both nuclines cross. So we have 1 here, we have 1 here, we have 1 here, and we have 1 here. So where is the fourth one? The fourth one would be if I project these nuclines to the fourth quadrant, which is not meaningful for us because it means that U2 is negative. So for these conditions, if A12 is bigger than 1 and A21 is smaller than 1, the fourth fixed point doesn't have biological meaning. I only have 3 fixed points with biological meaning. And what are those fixed points? The 0, 1, the 0, 0, and the 1, 0. Okay? Let's try to do now. I'm going to, if I can, which I couldn't. Let's now try to use this same graphical analysis to get an idea of the stability of these fixed points, which are the ones that we want to study. So what we have to do now is we have to think that we have here in our phase space U1, U2, for each value of our non-dimensional population sizes, we have a U1 dot U2 dot, right? So we have we have a vector field in our two-dimensional phase space that is going to tell us what is the rate of change of the populations. So for instance, let's have an example. We have our system. U1 dot is equal to F1, U1, U2, and U2 dot is equal to F2, U1, U2. If I say, okay, I'm going to say that U1 is equal to 0, and sorry, U1 is U2 is equal to 0, and U1 is positive. So somehow I'm going to be here in my phase space. Okay? If U2 is equal to 0, I already know, but because of the definition of nullcline, that's why I chose these values to cheat a little bit. I already know that U2, the derivative of U2 is equal to 0, right? Because it's a nullcline, it doesn't change. I'm on this line. It's a nullcline. Sorry. It's a nullcline for U2. U2 doesn't change. But what happens with U1? Okay, I can come here to my equation, and I can plug the values that I have. And here I'm saying larger than 0. You can say, I don't know, 0.1. And we plug the value with the A12 that we have, and we get a value, a number, that you will see that it is going to be positive. That means that if U1 and U2 are in this line, the change in the population size is going to be in this direction. Okay, why? Because U2 doesn't change. That means that I don't move vertically, right? If U2 is equal to 0, it has to stay 0. I cannot grow it down, cannot be, because negative cannot be. So I'm moving in this direction. Now, I'm going to move to the right or to the left. If the time derivative of U1 is positive, I'm going to move to the right. My population size is going to grow. So what's going to happen is that my population is going to move, my system is going to move along this line, and it will reach this point. And then it will stay stationary. If you do the substitution here, and you get that U1, the derivative of U1 is negative, then if you stay here, you would move to the left, and you will end up in extinction. Okay, is this clear? Because now we're going to make it a little bit more complicated. Okay. So now, guys, you can repeat the same. You can take a value in this other line, and you will do, following the same arguments, you will see that the arrow points in this direction. It's basically the same behavior. U2 is going to grow, and I don't have U1, and it's not going to grow. So now I'm going to ask you something that is going to reveal us how much everyone is following these arguments. And I want you to try to answer it. If I come here and I take U1 positive and U2 positive, but always below, still below this nullcline, okay? What is the direction at which, what's the direction of movement? Is going to be positive for U1 and positive for, sorry. Is it going to be positive for U2 and positive for U1? Is it going to be negative and positive? Is it going to be negative and negative? There is nothing I can say. What do you guys think? You can write in the chat, you can speak, you can answer in the way that you want. I want ideas. How would you do that? If I tell you, what is the value of these derivatives when U1 is equal to 0.01 and U2 is equal to 0.01? Supposing, again, that this point lies in this triangle here. What would you do? If you don't follow this geometric argument, how would you attack the problem?
we can substitute in the equation and verify the sign of the derivative.
Perfect. That's the way to do it. I plug these values here, I calculate the value of the derivative, and then I would get, I don't know, wherever I do, and I get the flow. That's the way to do it with my equations. But there is a trick to do this. I don't know if someone sees the trick. If someone does, please share it with us before I reveal the trick. No one? Okay, I will reveal it then. Lucas, yes, I listened some noise. Please. Don't tell me that you were unmuting yourself just to make me.
Well, I was gonna say something.
Okay.
I don't know if it's what you mean, but when the point crosses the green diagonal line, kind of flips the sign. Does it have anything to do?
Exactly. That's perfect, Nicholas. What is the definition of these lines? The definition of null line. The null line is the line over which, and now I don't remember, blue was for U1. Yes. In this line, the derivative of U1 is 0. It's the definition of null line. So if I don't cross it, here it's also positive. That's why I was so insistent by saying it's always here if I don't cross. But as soon as I cross this null line, then I change the sign of the derivative. It's the same that we were discussing yesterday when I told you guys, as soon as you know the stability of one point, then you cheat. You just alternate stable and state in one dimension. It's the same. And for the derivative of U2, here is the same. For derivative of U1, sorry. So here is the same. And actually, sorry, I did a mistake here. This was what was confusing me. So the mistake that I did is that when I cross the derivative of U1, I change the derivative of U1, okay? Not the derivative of U2. So it's the horizontal one, the one that flips. And here, the derivative of U2 stays positive, and when I cross the null line of U2, I flip the derivative of U2. And here, because I didn't cross any derivative of U1, I don't. So this is a way to reconstruct how the U1 and U2 will change depending on where we are in the phase space. Okay, and this already tells us, I mean, now with some imagination and of course we are going to get a sketch, we are going to get something very approximated, but we can already see that, for instance, when I am around this extinction point, I am going to leave it. So if when I'm here, this looks like this, when I'm here, this looks like this. So maybe my system is going to do something like this. If I start here, it's going to follow something like this. More or less, of course, to do it well and reconstruct this trajectory as well, I have to evaluate my equations and I have to reconstruct the vector field using evaluating the equations. But you can get a qualitative idea of what's happening more or less. So what you can see, for instance, already is that this point is going to be unstable, right? And this point here is going to be stable because it's going to attract a lot of trajectories here. So who has any question up to here? We're going to see this now in a clear way with figures that are not a mess. But who has any question about how to elaborate these diagrams by your own? It's not trivial. If it is the first time you see it, you will have to sit down, think about the null lines, think about changes in the direction of the derivative. I mean, it has some thinking behind. It's not trivial to, at least to me, it's not trivial. No questions? Okay, so, yes. So 1, 0 is metastable. That's what I want to show you now in the figures, because here it's already very messy. But you have kind of an idea already. It's not metastable, but the stability is weird, right? Because here it is attracting the dynamics, but here it is repelling it. I think that's what you are maybe meaning by metastable. We are going to give it a word to that. Yes, Nicholas.
I was gonna ask something that you're gonna show already, but it kind of seems like it's reflected on the U1 equals U2 line.
Mm-hmm.
No, I don't know how it would appear like algebraically.
So we will do the calculation to get exactly the directions in which is unstable and unstable, doing the analysis. But the idea is that in one of the directions it attracts, and in the other ones it repels. So the name of that is saddle point. We are going to see it in 30 seconds. So Enzo is asking if I didn't quite understand why crossing the null lines changed the direction. Sorry if I missed it. No. That's very important, Enzo. So it's very important that you asked. So the idea is that, and now let's see if I can. Okay, I will put it here, and then we will delete it. So the idea is that the definition of null line is that it is a curve on the phase space where U1 dot is equal to 0, right? By definition of the null lines. Do you agree, Enzo? You can write in the chat, or just, yeah. I just want to make sure that I don't lose you. Okay, so far so good, perfect. So I calculated my derivative, the direction of U1 in this line, if you remember. I can do that. I can go to my equations. And if I put U2 equal to 0, I can calculate the value of U1 dot. I can calculate it very easily, actually. So now the idea is that in this line, U1 dot is going to be equal to 0. So if I am here, this is going to still be positive, maybe positive but smaller, positive, assuming that it is smooth. Then eventually it's going to cross 0, and then here is going to be negative. Mm-hmm. If I cross this pink line, nothing happens to the derivative of U1 because it's at U2 null line. So now I have nothing to do with U1 dot. If you do for the derivative of U2, you will get the same. Here it's going to be positive, positive, and eventually it's going to be negative. Is it more clear now, Enzo? Perfect. Great. So more questions? Anyone? No? Okay, so let's jump to the figures. Okay. So here I am representing with red dashed lines. I'm representing the U1 null lines, if I am correct. Sorry, I'm very bad for the indexes. Yes, the U1 null lines, because it's the one where U1 is equal to 0 is a U1 null line. And with black lines, I'm representing the U2 null lines. Okay, so this is pretty much this, but well done. The lines that you see in blue is the numerical evaluation of my vector field. Okay, the only thing I did was I defined a grid, and in each of these points, I calculated the vector and I plotted it. Okay, this is telling me exactly the direction of my trajectories. For instance, what I'm doing, what I'm showing you guys in this second plot is what happens to a trajectory that starts here very, very close to the origin. What happens is what we said, it will follow the lines and it will end up in this fixed point. This is a plot in the phase space, U1 versus U2. Of course, this has some population dynamics behind that you can calculate if you integrate your system of ODEs, for instance, with some numerical method, or if it's analytical, you can get the solutions. If you solve this system, then you guys will get U1, U2 as a function of t, or tau in this case, and U1 as a function of tau. This is how my population grows and gets extinct and grows. As you can see, the information is pretty much the same. In the beginning, both trajectories grow. What does it mean? It means that in my phase space, I take this direction of movement. Eventually, U2 keeps growing. U2 keeps growing, but U1 starts declining. U1 starts declining. If I start, for instance, here in the phase space, I will have this trajectory. And this will have another representation in terms of the actual population dynamics that you see in the experiments, okay? So regarding the stability of this second point that we said, this point, we will come back to this type of points in a second. They are called saddle nodes because they are stable in one direction and they are unstable in the other direction. We can calculate the direction the direction of the stability and the non-stability using linear stability analysis. This will relate with the eigenvectors of the matrix of the system. We will get to that in a while, or maybe tomorrow, looking at the time. But we can get that. Sometimes people don't use it that much, at least for applications into biology. People that work with dynamical systems, of course, they use it more often. But you can calculate that, and it is there. So as you can see, I call this case competitive exclusion. So I want to jump a little bit back into the ecological meaning of this result. What is this telling us? So what this is telling us is that when A12 is larger than 1 and A21 is smaller than 1, unless I start without individuals from the population 2, which would be this case, my system will always end up with the elimination of the species 1 and the fixation of the species 2. So the species 2 will always exclude, will always outcompete the species 1, unless it is not present in the system in the beginning, which makes sense. If we move here, we are working with a system that we studied yesterday with the logistic growth. It's a projection of it's a one-dimensional projection of our two-dimensional system. But what does it mean, this specific relationship between parameters? Let's write it a little bit here. So let's see, try to understand what is the meaning of A12 larger than 1 and A21 smaller than 1. So here we're going to face the problems of working with non-dimensional parameters. And we're going to see how undoing the non-dimensionalization is going to give us information that from this is super hard to say. Although, well, in our case, it's not that hard, but I want to unfold the math so you see what happens when it is not so clear. So first of all, what does it mean that A12 is larger than 1? So if you guys remember from the definition of the non-dimensional variables, A12, I defined it as gamma 12 R2 over gamma 21 R1. You can go back to the notes and you will see that that's the definition. And that means that gamma 12 over R1 is larger than gamma 22 over R2. For the second condition, A21 is smaller than 1. If you recover the definition of A21, that means that gamma 21 R1 over gamma 11 R2 is smaller than 1, which means that gamma 11 over R1 is larger than gamma 21 over R2. So let's see if we are lucky enough to have written the equations using these parameters. Yes, we did. No, it's where is it? Gamma. Yes. So here you have to, if you consider the definitions of the alphas, and you put the definition of the alphas, and you put the definition of the current capacities, you will see that these coefficients here are basically these coefficients here, okay? So basically what these two conditions are telling us is that I'm going to use 1 star for this and 2 stars for this. So 1 star is telling us that for this value of A12 here, the species 2, remember that the order of the indexes, the species, this gamma 12 is the strength with which species 2 inhibits the growth of species 1. So it's telling us that species 2 inhibits the growth of 1 stronger than herself. And this 2 stars condition is telling us the opposite. It's telling us that species 1 inhibits its own growth stronger than the growth of 2. Species 1 inhibits herself stronger than how she inhibits the growth of 2. So with these conditions together, then the idea is very easy to understand. If I have 2 species and I compete with myself, I kill more of my cells. Sorry, I kill my cells more frequently or faster than what I kill cells from the other species, and the other species kills my cells faster than their own cells. It makes sense that the one that is killing herself very fast and is killed by the other one faster is going to disappear. So these are the conditions. This is how these mathematical conditions translate into relationships between interactions between different species. Okay. So there are, as I said, this is the first case. There are many other cases that I want to I want to discuss with you, so you get an idea of their meaning. But I think it's better if we discuss them with the figures that are already put in a pretty way instead of repeating all the analysis. So the other cases, of course, are going to be related to the values of A1, A2. So for instance, the case 2, we're going to call it to the case where A12 is larger than 1 and A21 is larger than 1. Sorry, this is case 3. Case 2 is going to be the inverse, the opposite case of case 1. So A12 smaller than 1 and A21 larger than 1. We are not going to discuss this one because probably you already imagine that it's going to be the same thing, but switching the role of species 1 and species 2. So nothing very interesting. And the fourth case is going to be that one in which A12 is smaller than 1 and A21 is smaller than 1. And these two, I do want to discuss them a little bit more in depth. So to make this discussion more fruitful, I want you to remember that these conditions on A12 and A21 are nothing else but relationships between the strength at which a species 2 inhibits the growth of a species 1 with respect to herself, and a species 1 inhibits the growth of a species 2 with respect to herself. So this is why these A coefficients are very meaningful, because they are giving me relative strengths of competition. So we are going to see what happens in cases where both species inhibit, let's see if I do it right. If I don't, please correct me. In cases where both species inhibit themselves we're going to see what happens in cases where both species inhibits their partners more strongly than themselves, which will be this case. And we are going to see what happens in situations where both species inhibit themselves more strongly than their partners. So what happens in these cases? We already know that if one of the species inhibits themselves more strongly than the partner, and the other one the other way around, we get to a competitive exclusion. So we're going to see what happens in the other cases. So we are going to start with case 3, that I want to hide the title so we don't see it. In this case, that remember is the case where A12 is larger than 1 and A21 is also larger than 1. In this case, because these crossing points were given by the inverse of these coefficients, these crossing points are always going to be smaller than 1. So in principle, the slope of my null lines is going to allow the existence of this coexistence point, right? If I have lines that go from 0 to a number that is smaller than 0 2 times, I get this crossing point in the middle. This is just geometry. But if we redo the phase space, what we see is that the stability of this this coexistence point is a saddle point, is a saddle node. Is what we said before, that had one direction that was stable and one direction that was unstable. So therefore, trajectories never really hit it. They get very close and then they somehow feel the repulsion and they leave. Okay, so this we will go to these saddle points probably tomorrow now. So, okay, in this case, what happens that is very interesting is that, as you can see here, depending on where I start with respect to this separatrix line, with respect to this direction of in the phase space, sometimes my trajectories will go to one of the fixed points, and sometimes they will go to the other fixed point. So basically, depending on the initial condition that I choose in my U1, U2 phase space, the fixed point is going to be one or the other. I have what is called bistability. So both points are stable, but as compared to this case, where the whole phase space, unless this line, okay, but the whole phase space was a basis of attraction to this fixed point. Now, my phase space is divided into 2 different bases of attractions for each of the fixed points, which makes sense, because if both species inhibit the growth of their partner more strongly than what they do with their own growth, depending on the initial condition, I will end up with exclusion of one or the exclusion of the other, depending on how much cells of each type I have. Okay, and you can do, as we said, we can solve the ODEs, and you can see that depending on the initial condition, so this is the population size versus time plot for this green line. So if I start here, you see that initially both grow, but then species 2 dies and species 1 goes to 1. But if I move my initial condition just a little bit, notice that here on purpose, I am starting with the same number of cells from the population 1, but I'm just adding a little bit more of U2. Then I am giving more strength to U2 to kill U1, and the behavior that I observe is completely different. Now, They both grow in the beginning because the population size is very low and the quadratic terms that I have in my equations don't play so much role. But then as far as I get some large population size of the species 2, the competition with the 1 is so strong that it starts killing. Okay? And I get this kind of bistable exclusion. I still don't get coexistence. I want to make it clear. I still don't explain my experimental result. I always end up with 1 or 2. But what it is very nice is that if I repeat this experiment many, many times, depending on how precise I am to construct my initial condition, and depending on where I start. So for instance, if I start in this region here with very few cells, which is something that is very common in experiments, depending on the precision that I have to make my mix, I may sometimes see this process, and sometimes I may see this result, and sometimes I may see this result. I can see the bistability of my system if my system has this kind of interactions. Okay. Of course, this is assuming that the dynamics is entirely deterministic. If you have noise in the population growth, you can see that these trajectories are not going to be so smooth, and sometimes fluctuations can take you out from the basis of attraction of one fixed point and take you to the other, and noise plays a role. But we are forgetting about that. Remember, we are working with the mean number of particles, okay? So Victor Hugo is asking if U1 and U2 will never be in the point where the nucleons cross. They will never get there unless they start there. So remember that that's still a fixed point. If I am so precise that I start, so if I take my ODEs and I integrate them with an initial condition that is this fixed point, the system will get there, will stay there. I will see that my populations don't change in time. But if I don't start in that precise point, they will not. If I start here, they will go here. If I start here, they will go there. Okay, because it's a fixed point, but it is not stable. You will end up in that fixed point if you start in the value. That's important, because sometimes when we say, this fixed point is unstable, we tend to believe that then the system will not stay there. It will stay unless you perturb it. Okay. So let's move now to the fourth case. The fourth case is the one where we have, as we said here, is the one where we have both coefficients to be smaller than 1. And we're going to see what happens in that case. So in this case, both nucleons, because let's write our conditions here, because A12 is smaller than 1 and A21 is smaller than 1. A12 is smaller than 1 and A21 is smaller than 1. Then these crossing points now are larger than 1, because remember that this is the inverse. So the point still exists. It's still in the first quadrant. But as you can see now, the vector field is a little bit different. So now these points are unstable or are saddle nodes, and the flow, and actually is here, the flow of the vector field, of the vector field goes to the point of coexistence in these trajectories or in this one or in any trajectory that you can imagine. So now this fixed point is stable. Any trajectory that starts with, sorry if sometimes I'm abusing a little bit of the language. If when I say that any trajectory will end up in here, I'm assuming that we don't start in these extreme cases where I don't have one of the species. Of course, if I don't have one of the species, there is no magic here, so I cannot create it. I'm assuming that I start inside the phase space, no in the axis. So you can see that any trajectory will end up there. So you can see that no matter where we start here, this is again the time series for this blue trajectory, the time series for the green trajectory. I always go to this condition. And of course, the value of this fixed point will depend on the actual value of A12 and A21, as far as they are smaller than 1. So if it is not the same, them to be 0.1 and 0.3 or 0.2 and 0.8. So this fixed point, of course, can move around the phase space depending on how I precisely parameterize my system. Okay? So what is the take-home message from all this analysis? The take-home message from all this analysis is that if I want to get coexistence, which is the experimental result that Gauss found in his experiments here, I need my species to interact between them in a way that they inhibit the growth of their partner, they inhibit their own growth more strongly than the growth of their own partners. Or in terms of intra and interspecific competition, I need intraspecific competition to be stronger than interspecific competition, which makes sense. If I want to coexist, then I need to fight with my rival. Well, depending how you define rivals. Here, everyone is a rival. I have to find to compete with other species more strongly than with my own cells, or cells from my own species, to be more precise. This is one of the ways to get coexistence of a species. There are tons of them, and probably if you have if you're more familiar with biology, you can think of them. There are ways, for instance, when I have a space, you can tell, okay, but here you're assuming that cells can find each other everywhere. What happens if a tree, as we said yesterday, a tree is in Rio and the other tree is in Sao Paulo? Okay, they don't interact, so the space is also dividing resources. Or what happens if some animals decide to hunt in the night and other animals decide to hunt during the day? Okay, they divide the amount of prey. One takes the day prey, the other one takes the night prey, and they can coexist, for example. That's another way. Or what happens if, I don't know, one specializes on eating some food and the other one specializes on eating another food? That also explains coexistence. What I want to say is that this is a situation that can explain the coexistence of these two species. And it is a model that recovers very well the conditions that we saw in the experiment, because we're assuming everything that is well mixed. Remember that everything was in a bottle. We have two species of yeast, so we can think that they kind of like the same types of sugar. So for this specific experiment, this is a path to explain coexistence. Of course, it is not the only one. There are ones that are way, way, way more complicated than this one. So I don't know, guys, if yes, are oscillatory solutions possible in the two species model we are considering? Guilherme, the answer is, if you say in the two species model we are considering, no. If you say in two species models, then yes. So for this, what I want to say, for this specific type of interaction that is competition, remember, our equations are the ones that are these ones. I don't get oscillations, assuming that I have this model. In the case where I said that if you somehow put some time dependence, saying this animal hunts in the night, the other one hunts in the day, you will probably get oscillations, day-night oscillations that are imposed by this behavior. But in 5 minutes, we are going to go to a situation where you can get oscillations in this very simple model. So I will leave you with the how do you say that in English? With the intriga until for 5 more minutes, and then we are going to resolve it, if you allow me. But yes, you may get oscillations, and those are much more fun. Yes, Amanda.
Ricardo, it may be a silly question, but I was wondering that B stability, it's only a result of how you relate the parameters. So any model can have B stability, or there are some conditions for how you write the model that would allow for B stability to be possible.
Yes, so bistability, so let's see, I'm going to explain it maybe in a very mathematical way. And if it's too mathematical, please tell me, not only you, Amanda, anyone that finds it too mathematical, and we try to reformulate it a little bit less mathematical. So there are, basically the idea to have bistability is that you need, so you can also, you can have it either in two-dimensional models or in one-dimensional models. So in that sense, it does not depend on the number of equations that you have and the type of the model. The idea to have biostability is that you need two different fixed points that are stable, right? And they need to be divided. In the middle of both of them, you need to have some point that is either unstable or a saddle point. So you need to have some sort of interaction. In this case, it is the intensity of the interspecific versus intraspecific competition, but it can be, for instance, something that is called a Lie effect, that I think I'm actually going to touch on it today very briefly, that tells you that depending on where you start with your population sizes, the outcome of the interaction can be one or the other. So this may be, for instance, if you think in terms of sexual reproduction, that may very easily come from the fact of having very few males or very few females. So to the fact of needing some critical population size for the population to grow. Here we have that cells divide, no? They divide, so as far as I have one, I have two, I have four, so on and so forth. If they need to mate, to reproduce, then maybe if you have one male and one female, they don't mate before they die. Or if you have three males and one female, or one male and three females, sorry, I think I said the same twice, or three males and one female, maybe the reproduction does not happen fast enough for the population to take off, and then it eventually dies. So usually biostability is related either to density dependence on the strength of the interactions. That would be the less mathematical way, I would say. I don't know if that makes sense. So if I gave one of these two long, non-clear answers, please tell me.
Yeah, I understand. So basically you have to incorporate processors in which would make the population go to zero, like in Lie effect, and others that will make populations go to the carrying capacity. So you have to have this gray zone in which the system will go either to carrying capacity or to extinction.
Yes, that would be one case. In our case here, for instance, for two species, we don't have, we don't need that critical value of the population size. We don't need that threshold kind of population, although somehow we do have, no? Because what in our case, the threshold of the biostability would be given by this line here of the saddle node, right? So this would be kind of a threshold. If you start here, species 2 survives. If not, dies, because it's not strong enough to kill species 1. Instead of being strong enough to reproduce successfully, it would be in terms of the presence of the second species. But it is always related to some having to overcome some critical value of the population for you to succeed, basically.
Thank you.
Thank you. Okay, more questions? So guys, I was planning to do the formalization of the stability of the fixed points in 2 dimensions, but that's a kind of a long calculation that I don't think I will have time to cover today. So tomorrow we are going to talk about discrete in time models, and I think that one is going to be less math and short. It's going to be more intuitive. So I think I'm going to skip that big calculation for tomorrow. Anyway, it's not going to, it's more a formalization of the concept that we've seen graphically. And now I want to touch a little bit, well, first answer more questions if you have, please ask them. And I want to touch a little bit on this idea I said in the beginning of how to extrapolate these models to other interactions. I owe Jayme an answer. I haven't forgotten about the existence of oscillations in these models and this kind of ideas. So if you have questions, guys, we have this time. I'm not going to go to the big, well, big. Those of you that are used to, I don't know, quantum mechanics calculations, maybe it's not that big, but it got some steps and stuff like that. So more questions before we generalize these interactions. No? Okay, so if there are no more questions, I want to touch a little bit, let me find it here. Touch a little bit on how to go beyond competition of yeast to use this model. So remember that we started the lecture today by saying that we were going to study a species white, or species 1, and species pink. Species 2, and we said that we were going to use this kind of, I don't know if network-like, but at least in terms of nodes and links representation. And they were inhibiting each other. We said that this was going to be a competitive interaction. Competition. So for many, many times, competition was thought to be like the I don't know if the most important ecological interaction, but it was not overstudied, but many people were studying competition. This idea of why I have so many species coexisting if they compete. But there are many other interactions that are equally important. So for instance, we have a type of interaction that maybe is more familiar to those of you that haven't studied ecology that much, but are curious enough to read about it. That is a prey-predator interaction, where the presence of one of the species favors or allows for the growth of the other and the growth of one of the other answer. Species 1, let's say, the white species inhibits species 2, it eats on it, it feeds on it, and species 2 is the food for species 1. For instance, a fox and a rabbit. So in this case, this pink species would be the prey, and this white species would be the predator. This type of interaction is also happens in infections, for instance. This would be a host, and this would be a parasite, where the parasite needs the host to grow, and by parasitizing it, it inhibits its growth, or it reduces its growth, okay? So these type of interactions, as you can see, we can pretty much study them using the same formalism we've developed, but now we have a small difference, which is this sign of this interaction. And we will see how to put that in the equation in a while. But before that, I want to put a third type of interaction that I find very, very interesting, and that maybe many of you also know already, that is one in which a species 1 helps, or species 1 favors the growth of a species 2, and a species 2 helps the growth of a species 1. So this kind of interaction that is called mutualism sometimes can also be understood as cooperation. You help me, I help you. Is typical, for instance, of plants and bees, where the bees take pollen from the plants and help pollen and help them disperse their pollen, for instance. And it happens in many other examples in nature. It happens even in tiny microorganisms that you don't see, which to me is fascinating. This is one of the things, for instance, we work in my group in ICTP. We study in our group in ICTP. We try to study how this kind of mutual cooperation between individuals, why is it evolutionarily stable? If in principle doesn't make sense that, I mean, if you are going to help me, I don't help you. I take your help and I run away. Why I will help you? You can find your way, no? That would be the kind of explanation that one would expect from the ideas that we usually get from evolutionary theory, no? That the one that gets more of, doesn't make sense to sacrifice your own reproductive success to help someone else. So this is another example of ecological interaction. So how can we generalize our model that, remember, was a super simple model, although at this point I hope I already convinced you that it's simple but still powerful and pretty. How can I extend this to account for these behaviors? And I want to hear ideas. I'm already speaking too much today, so ideas about this, please. Any idea? Okay, I'm going to use some color that we haven't used so far to indicate this. So, any idea? No? Ah, sorry, I have to follow the chat. Rafael, thank you very much. Changing signs, exactly. If you guys think what these equations are telling me, remember that when we wrote the very, very simple model the first day, which was yesterday, where we said that, you see, I'm speaking too much. When we say this, we said that this was the growth rate. And you can plot it. You can say, okay, if R is positive, my growth rate is like this. If R is negative, my growth rate is like this. And if R is equal to 0, my growth rate is 0. Okay, I'm just saying that this is f of n and this is f of n. So now, because I have two species, I still can interpret this as the growth rate of species 1 and this as the growth rate of species 2, right? Nothing tells me that I cannot do that. The only difference is that now the growth rate depends on U1 and U2, and I will have some heat map here going, I don't know, from blue to yellow. Right, but in principle, this is giving me the growth rate of U1, how fast the population 1 grows if I have some individuals of 1 and individuals of 2. So what I was saying is that if I have another type of interaction where the presence of 2 helps the growth of 1, basically the only thing I have to do is to change my signs here, right? Or if I have a prey-predator interaction, I only change one of them. Okay, so this is a kind of a straightforward way of accounting for these different interactions if I have two species and I have all these different types of interactions. Of course, there are many different ways to do this. There are some models that do not account for this term and for this intraspecific competition, and they only account for the benefits of predation, and there are many ways of modeling this, but the general idea is that this is the growth term of species 1, this is the growth rate of species 2, and if I want to account for other interactions that are not competition, the only thing is that the contribution of the species that is not a competitor has to be of the sign that it is in nature. That's the take-home message. Of course, changing signs here sometimes leads to mathematical problems and makes us having to modify it a little bit, the growth rates to have them well behaved. For instance, I don't know, you can imagine that if I assume that these guys cooperate with them and with themselves and with the others, so we have something like this. For instance, everyone cooperates with everyone, and all these signs are positive. This will exploit, for instance. This is mathematically nonsense, which also makes sense. At some point, I need to have some limitation of this growth. Even if I am an extremely cooperative person, at some point, there is some, I don't know, even if it's finite space, something has to saturate this growth. So that usually these models are modified a little bit to take into account these things. If you are interested in learning about generalizations of this, there is a very good book that is called Mathematical. I think I can write it in the chat. That's better. Mathematical Biology by Jim Murray. And in the volume 1, I think it's chapter 4, they extend this. At least he works the mutualistic interaction fully. Okay, so that's a good reference to study about this. Also, going back to your question, Jayme, and tomorrow we will see the general conditions to have oscillations. In prey-predator models, you may get oscillations. So something I forgot to say is that this model that we are working here is called the competitive Lotka-Volterra equations. And this is in fact a generalization to competition to a model that was developed initially to study prey-predator interactions. So with prey-predator interactions, you do get oscillations. You do get oscillations with your model, and you do get oscillations with in real data in nature. So let me see if we can do something. While you guys, if you guys have some questions, now is the perfect moment, because I had Jayme waiting so long that I want to show him an actual oscillations, both in a model and in data. So questions?
Hey, hello, I have a question.
Sure.
You motivated your talk showing us two databases of the different cells, and you developed that model. But I have a question in related to that model that you developed. Does it fit the database of that original motivation?
Okay, that's a very good question. So in principle, it does. So this is, for instance, for the case of one species, it does. But this is like a very, very simple experiment. Usually, people can do things like, I mean, they can explain behaviors fitting this model to data, but it has a lot of limitations. So this is a very active line of research. I'm trying to understand situations that are more complex that we will see tomorrow. I think we don't have a very strong empirical example motivating us. It's more, I want you guys to see how chaos emerges, because I think it's a pretty thing. But the day after tomorrow, we have another example that is, for instance, the invasion of a rat on Europe. So it was a rat that arrived in the beginning of the 20th century, and we're going to see how it was taking space as time was going by. In that case, we need a different model. So for this simple experiment, it does, but it's very, very limited. It's a toy model, so we have to be careful. So before we jump to the thing I want to show you guys, of course, you may be thinking that, of course, we have two species, and this is also related to your question, Roberto. I have two species in a bottle, very funny, super easy, but when I go outside, I don't have two species. I have many of them. So what I'm showing you here is a more complex scenario where we have a lot of different species that are interacting with each other, and this is what is called a food web, which basically encodes a lot of prey-predator interactions. So for instance, here in the top, you have what are called the apex predators, or the top predators. For instance, the fox is not eaten by anyone, but it's able to eat rabbit, to eat mouse, to eat titmouse. And then the mouse, it's eaten by the buzzard, which is this big bird here, by the fox. But the mouse eats plants. And so there are ways to increase this to much more species. Of course, at the end, what we have is, instead of 2 of these, we have 20 of these, we have 30 of these. And the question that we want to address is, how can we explain the coexistence of these 30 species together? Of course, in that case, writing the phase space does not help. Having the nuclines maybe is not so easy, unless you work in string theory. In that case, I think you maybe are better with 15 dimensions and 20 dimensions. But what we do is we generalize the analytical framework that we are going to see tomorrow. And that's why, despite it may be a little bit tiny mathematically, I want you guys to see it, because that framework is going to tell us the conditions for us to understand the stability of these fixed points analytically, working with the matrix of interactions in my system, with the coefficients of interactions in my system. And that's going to tell me how, depending on the signs and the values of those parameters, I can predict the stability of my fixed points and the stability of my communities. So and I think this connects also with some of your questions. The answer is, these models they work, they are useful, they are interesting, but they are far away from the complexity that we see around. So unfortunately, I am not a big expert on this. I think it's a very fascinating topic. I just I haven't studied it so much. There is a PhD student that I work with he works on this. He's super interested on this, and this is something that is interesting me more. But if you have more precise questions, I am afraid maybe I won't be able to answer you, but we can ask Rafael, who is the name of this student that works on this topic, which is a very interesting one. So take home message from this: 2 species are nice. They allow us to build intuition. Real world is more complex, and we need more powerful mathematical and computational approaches to understand. With this, I just want to show you the famous oscillations, because otherwise I think I will lose as many people for tomorrow. I will stop sharing here, and I have to start sharing here. Yes, perfect. Now, I think now you guys can see my computer screen, right? Perfect. So let me see what we have here. Okay, so this is nothing else but what you already saw, guys. This is the experiments, the model, simplified way, boring. But now, sorry, what are you seeing? You are seeing the good way or the comments?
We're seeing the comments.
You didn't tell me. This is we're recording this, guys. We cannot do, okay, I think now.
Yeah, perfect now.
Perfect. Thank you, Daniel. You saved my my recording. So in the 2-dimensional case where I have prey predators, you can see already the different signs in my model. Here you have one equation with a negative species 1 is inhibited by the presence of species 2, and species 2 is fostered by the presence by the presence of species 1. This means that 2 is the prey and 1 is the predator, right? So this plot that you see down here with the orange background, this is a time series that goes from 1845 to 1935, so it's almost 100 years of data in Canada, where they were counting the number of hares is, I think, is a type of rabbit, and the number of lynx in that region. And they were seeing that year after year, there were these, of course, noisy oscillations, but this is very clear oscillations to be real ecological data. So there are oscillations in natural systems. And actually, you can see that, for instance, the peak of the blue population is always before the one of the red, which makes sense because you can imagine that first prey grow, then predators have a lot of food and start growing because they have food, but then they die. So the phase of the oscillations can be also explained. And with this model, playing with the parameters properly, with guided by the analysis that we will see tomorrow, you see that we recover these pretty oscillations as well. And these are stable oscillations that sustain in time forever. They are not damped or something like that. So tomorrow we'll see what do we need to get these oscillations. But since I remembered I had the plot done, I wanted to show it to you, so it was more clear my answer. So Amanda is saying that another way to put limits on mutualistic interaction is looking at it as mutual exploration, expliciting the actual mechanism that the species are helping each other, like in this paper from Fernanda Baldovinos. Okay, I didn't know about this, but I will also read it. Thank you very much, Amanda. Yes, Naila.
Did you get the answers about the class, we call it class?
About the, sorry, Naila? You can ask in Portuguese if you prefer. Right? It's, I remember that the questions.
Aulas gravadas, as aulas gravadas.
Sim, desculpa, eu achei que não, é que assim, as aulas já estão no YouTube no mesmo dia que nós acabamos as aulas. A aula do...
The link of YouTube?
Let me see. Vou colocar no chat agora. Vocês...
I didn't receive any email about it.
So it was my fault because I sent you guys the thank you very much, Rafael.
Okay.
It's in the, so yesterday I got an email from one of you, I think it was from you, Nicolas, actually, telling me the lecture is already in, and I thought it was a replay all, And then I thought, perfect. But they are already there. So actually I will, well, that's fine. They are already there. They are uploading them as I send them to Patrick, to the organizer.
In your slides, it's in the Dropbox?
Yes. So what I'm going to do today, I'm going to convert the notes to PDF and I'm going to put them in the Dropbox. And I wanted to ask you something about that, because I am noticing that I start very ordered and I start very willing to be clear as I write, but then I'm going to